The first review video ended up a lot longer than I intended, so I'm going to try to keep this one a little bit shorter. So the part one of the review video covered section 1 and 2, and I reposted the video I had made for section 3. So in this one, I just want to cover some things in section 4 and section 5 really quick. In section 4 and section 5, we talk about rational and radical equations, and then absolute value equations and inequalities. And the way that I like to think of these different equations is, how do we fix them? Our goal is to turn them into a linear or quadratic equation, because in chapter 1 we reviewed how to solve linear equations, and then in the beginning of this chapter we reviewed how to solve quadratic equations. So with the rational equations, rational means fraction. The radical equations, where we see square roots or cubed roots, we see that radical symbol. And then absolute value equations, where we see those vertical bars. We need to do something to fix them that will change them into linear or quadratic equations. So our first goal is always to do something that will transform them into a linear or a quadratic. So the first few problems here are rational equations. And with rational equations, the problem is we've got variables in the denominator. So if those variables were not in the denominator, then we would just have numerators. And if you look at our numerators are linears and quadratics. So they're perfectly fine. So to fix these, we need to get rid of those denominators. And denominators signify division. So to get rid of division, we do the opposite. We multiply. But the trick is, we need to multiply by one thing that will cancel all of the denominators. So let me pick one here that can be representative of all of them. And I'm going to pick this one right here. So I'm going to copy this over onto my blank paper. It's 1 over 3x plus 12. Minus 3 over x squared minus 16. Equals 5 over x minus 4. So to fix this, we need to get rid of all the denominators. And denominators signify division. And to cancel division, we multiply. But we can only multiply by one thing through the whole equation. We've got to multiply everything by the same thing. And we want that one thing to cancel all the denominators. So what I'm going to do is, I'm going to go through and I'm going to factor all of the denominators. So this first denominator factors to 3 times x plus 4. The second denominator factors to x plus 4, x minus 4. And the last denominator, those two terms don't have anything in common, so we can't factor them. So if you look at those 3 denominators, we need to pull together those factors and figure out something that we can multiply by that will cancel all of them. So to cancel this first denominator, I need to have a 3 and an x plus 4. To cancel my second denominator, I need to have an x plus 4. I've got it. And I need to have an x minus 4. So I'll throw that in there as well. To cancel this last denominator, I need to have an x minus 4. Well, I've already got it. So 3 times x plus 4 times x minus 4 is what I need to multiply this entire equation by to cancel all of my denominators. So I am going to multiply through this entire equation by 3 times x plus 4 times x minus 4. And when I do this, what I'm doing is I'm essentially just taking that group of factors and just putting it into the numerator. I'm not going to multiply any of it out. I'm using it just to cancel my denominators. So this turns into, well, 1 times all that stuff is just going to leave me with that stuff. So 3 times x plus 4 times x minus 4 over 3 times x plus 4 minus, and here I've got 3 times 3, well that's 9, x plus 4, x minus 4 over x plus 4, x minus 4 equals 5 times 3 is 15, x plus 4, x minus 4 over x minus 4. So I have not done anything with my denominators yet. I've just taken this and I've multiplied it into each of my numerators. And our next step is to cancel as much as possible from the top and the bottom. So in my first fraction, the 3's will cancel and the x plus 4's will cancel. And the only thing I have left is x minus 4. And notice that everything in the bottom canceled. In my next fraction, the x plus 4's cancel, the x minus 4's cancel. All I'm left with is minus 9. In the third fraction, the x minus 4's cancel, so I'm left with equals 15 times x plus 4. So now I just have a linear equation to solve. So minus 4 and minus 9 is minus 13. So this is x minus 13 equals, and here I want to distribute. I've got 15x plus 60. And we're going to want to get our x's together. So I'll subtract my 15x's over. Just because I like to have my x's on the left. It really doesn't matter which side they're on. And add your 13 over to the right, and that will get our x's all by themselves. We get negative 14x equals 73, and then you can divide over your coefficient. We get x equals negative 73 over 14. With rational equations, you need to make sure that this number does not create any zeros in your denominator of your original equation. So if you look back at the factored form of your denominators, you need to ask yourself, what would make this equal 0? Negative 4 would make that 0. And our answer is not negative 4. So that one's good. That's the same factor. Negative 4 would make it 0. Positive 4 would make that 0. And positive 4 would make that 0. So if we had solved this equation and negative 4 or positive 4 came back as either one of our answers, we would have to just throw it away. We would not be able to use it, because if we were to plug it back in the original equation, we would get a 0 in the denominator, and we are not allowed to divide by 0. But our answer is not positive or negative 4. So our answer is perfectly fine, negative 73 over 14. So our goal with rational equations is to fix them. Our goal with all of these is to fix them somehow. And the problem is the variables in the denominator. Denominator means divide, and to cancel off divide, we multiply. But we've got to do it all at once. So we look at the factors in the bottom, and we try to come up with one thing that will cancel all of the factors. And we multiply through our equation by that. And when we multiply through, we only multiply it into the numerator. And then go through and cancel. And it should cancel all of our denominators. And it should leave us with just a linear or a quadratic equation to solve. Once we solve it, we need to check. And we need to check that this value doesn't make any of our denominators equal 0. So the other type of equation in section 4 are the radical equations. And we're going to do pretty much the same thing. We need to fix them. So with radical equations, the way that we fix them is we have to get rid of the radical symbol. And we've worked a little bit with radicals already. We've used square roots to cancel off squares because squares and square roots are opposite operations. So now we might have square roots already in the problem. So if we need to get rid of a square root, we will square to get rid of it. But it might not just be square roots. There might be cube roots or fifth roots. So any type of radical, any type of root in the problem, we're going to use an exponent to cancel it out. So the way that we fix a radical equation is we use a power to cancel the radical. Most often, though, the power is not your first step. You need to make sure that the radical is all by itself first. You want to isolate the radical as the first step of the problem. And the reason we need to do that is because when we put the power or this exponent into the problem, we can only put it in once on the left side of the equation and the right side of the equation. So if our radical has any other terms on the same side, then we're going to have to do some FOILing, and we don't want to FOIL with a radical. If the radical is all by itself, when we put a power next to it, then the radical and the power can cancel. So isolate your radical first, and then use a power that will cancel the radical. And we use that power once on the left and once on the right. And once that radical is gone, we should be left with a linear or a quadratic equation to solve. And you always need to make sure you check your answer. Because sometimes in the process of using the powers, especially with even powers, if we've got that our radical is equal to a negative, and you put an even power in the problem, for example, -3, when you square it, it changes to a positive. In the process of the sign changing, sometimes changes an answer that would have worked into an answer that doesn't work. So especially the problems where you use even powers, you might get answers that do not work. So you need to check your answer. So I'm going to go back to MyLabs Plus here and pull a question out of the homework. So it looks like those first 7 problems were all rational equations. And number 8 starts with the radical equations. And we're seeing all sorts of different kinds of radical equations. They're not all square roots. Some of these are a little bit trickier than the others. And then it starts with the absolute value equations there at number 17. And that's section 5. All right, so let me go back. So I'm going to do this problem right here because this one's a little bit trickier. Some of the other ones are a lot easier. So this is a good example of being very careful in with your algebra, being very careful with your algebra rules. So this one says the square root of x plus 64 plus 8 equals x. And be very careful because the plus 8 is outside of the square root. So our goal is to turn this into a linear equation or a quadratic equation somehow. But we see a square root in here, so we need to fix that. And the way that we fix that, I know that squares will cancel square roots. So at some point, I want to square this to cancel the square root. But I don't want to do that until that square root piece is all by itself. So the very first step here is to get the square root piece all by itself. So I'm going to subtract that 8 over to the right. And that will get my square root piece all by itself on the left. And then I'll have square root of x plus 64 equals x minus 8. So now my square root piece is all alone on the left. A square will cancel a square root, and you need to be really careful because when you use powers, you can only use them once on the left and once on the right, and you're applying the power to the entire side of the equation. So I'm going to square the entire left, and I'm going to square the entire right. On the left, the square and the square root just cancel, and we're left with the stuff that was inside, x plus 64. But on the right, x minus 8 squared, you're going to have to FOIL that. And if you FOIL that out, you get x squared minus 16x plus 64. So this one turns into a quadratic when we fix it. We've gotten rid of the square root. First, we isolated it. We got it all by itself on one side of the equation. Once it's by itself, we can use a square to cancel the square root. And then we're always left with a linear or a quadratic to solve. This one ended up being a quadratic. Anytime you solve a quadratic, you want everything on the same side of the equation so that the quadratic is set equal to 0. So I'm going to pull this stuff over to the right. So I'm going to subtract over an x and a 64. And I'm left with x squared minus 17x, and those guys cancel. X squared minus 17x equals 0. And that one's pretty easy to solve because we could just solve it by factoring out an x. And we get x equals 0 and 17. But we've got to check these. We've got to check these and make sure they really work. So we go all the way back to the original problem and plug them in. So the original problem said the square root of x plus 64 plus 8 equals x. And I'm going to replace the x's with zeros and see if that's true. So the square root of 0 plus 64 plus 8 equals 0. Well, 0 plus 64 is 64. Square root of 64 is 8. Is 8 plus 8 equal to 0? No, that is not true. We're throwing that answer away. And let's check 17. Square root of x plus 64 plus 8 equals x. And we replace the x's with 17. So 17 plus 64, 60, 70, that's 81. The square root of 81 is 9. Does 9 plus 8 equal 17? Yes, it does. So our only answer is x equals 17. So even though we solve our quadratic and we get two answers, one of them does not work. So you don't know that until you check. You have to check your answers. Only one of them really works, and there is only one answer to this problem. It's x equals 17. So with our radical equations, just like with our rational equations, the goal right from the beginning is to fix it, to do something that will turn it into a linear or a quadratic. So with radical equations, we've got to remember that powers and roots are opposite operations, and somehow we need to use a power to cancel the root. So we get the root all by itself. Once the root is all by itself, we can use a power that will cancel the root. We do it once to both sides of the equation. That's what keeps the equation the same as the original, and cancels the root, and then we should be left with a linear or quadratic to solve. But you've got to check your answers. I'm going to do one more of these because in your homework you had some that had two radicals in them. And when you have two radicals, that just means you have to repeat this isolate and square process twice. So I'm going to do this one. It says the square root of x minus 9 plus the square root of x plus 6 equals 5. So there are two radicals in that problem. We're still going to approach it the same way we just did the last one, but we've got two radicals to cancel. That means we're going to isolate and square twice before we're left with a linear or a quadratic to solve. So the square root of x minus 9 plus the square root of x plus 6 equals 5. There are square roots in the problem. We need to fix that. To get rid of a square root, we square, but we don't want to square until we have one all by itself. So I am going to move one of them over to the other side and deal with it later. So for my first step, I am isolating the square root of x minus 9. Square root of x minus 9 is isolated. Now to get rid of the square root on it, I can square. But in order to do that on the left, I also have to do it on the right. So on the left, the square and the square root just cancel. Now on the right, this is kind of tricky because that's a binomial. And if I'm going to square a binomial, I need to FOIL it. And foiling with that root is going to look kind of tricky. So this is 5 minus the square root of x plus 6 times 5 minus the square root of x plus 6. And we're going to do firsts, outers, inners, and lasts. And remember, you cannot combine stuff outside of a square root with stuff inside of a square root. All you can do is write them next to each other. So this is what this turns into. So on the left, I'm just left with the stuff that was inside, x minus 9. On the right, when I FOIL, 5 times 5 is 25. When I do my outers, I've got 5 times negative radical x plus 6. That's just negative 5 radical x plus 6. Now, I can't multiply the 5 into the radical. All I can do is write them next to each other. Now, when I do the inners, I've got the exact same thing. Negative radical x plus 6 times 5. So, minus 5 radical x plus 6. And then when I do the lasts, I've got negative radical x plus 6 times negative radical x plus 6. Well, I'm multiplying something by itself. That's the same as squaring it. So technically, I'm squaring something that has a square root in it. And it's a negative times a negative, so it's going to turn into a positive. And I'm squaring a square root, so I'll just be left with what's inside. So let me clean that up a little bit. We've got x minus 9 equals, I'm going to put my 25 and my 6 together. That's 31. I'm going to write my x next, plus x. And then these are like terms. I've got minus 10 radical x plus 6. So I have gotten rid of the root around the x minus 9. Now, because the original problem had 2 roots in it, that just means I'm going to have to go through this whole isolate and square process twice. So I isolated my square root x minus 9, and I squared, and that fixed that one. And now I'm going to do the same thing for this one. I need to now isolate the square root of x plus 6. So I want to get this one all by itself. So I need to minus my x over, which is nice because it cancels on both sides. I also need to minus my 31 over. And that gives me negative 40 equals negative 10 radical x plus 6. And then I'm going to divide my negative 10 over. That leaves me with 4 equals square root x plus 6. Now I've got my square root x plus 6 all by itself, and I can square both sides to get rid of that square root. And I've got 16 equals x plus 6. And we're just left with a linear equation to solve. So I'll minus my 6 over, I get x equals 10. And what do you have to do for all these problems? You have to check. We've got to plug this 10 back into the original, the very original, and make sure it really works. So the original equation said the square root of x minus 9 plus the square root of x plus 6 equals, and I forgot the rest of it, 5. So let's make sure that's really true when we plug 10 in. So the square root of 10 minus 9 plus the square root of 10 plus 6, does that equal 5? Well, 10 minus 9 is 1. 10 plus 6 is 16. The square root of 1 is 1, and the square root of 16 is 4. 1 plus 4 is 5. Excellent. X equals 10 is our answer. Now, if for some reason, when we solved this problem and we only got one possible answer and we checked it and it didn't work, then there would be no solution. Or if we got 2 answers and neither one of them worked, and we had to throw both of them away, then there would be no solution. And if you look in MyLabs Plus, that is an option. Option B is there is no solution. That means when you solved it, you got some answers, but then when you went back and checked them, none of them worked. So that's why you're seeing that, because just because you got an answer doesn't guarantee that it's always going to work. You need to check them. So this one is much trickier. We're still following the same process. It just takes a little longer because we have to do the process twice because there's 2 square roots. So you got to isolate and square, for the first one, and then isolate and square for the second one until you get down to your final linear or quadratic to solve for your answer. So that's section 4, our rational and radical equations. Section 5 is all about absolute value equations. And it actually talks about absolute value equations and inequalities. So we'll start with the equations, and then the inequalities are going to be very similar. And again, we're going to approach this as, how do we fix this? How can I turn this into a regular old linear or quadratic equation? So what makes this from the get-go not a regular linear or quadratic equation is that there's absolute values there. So if you know what an absolute value is, then you know that you can do the absolute value of -5 is 5. The absolute value of +5 is 5. So what that means is there are two different numbers that can give you the same answer, the positive and the negative of whatever that is. And that's how we're going to split apart our equations. So if absolute value of x equals a, this means two possible things. Then either x equals a, like in this case, they're the same thing, or x equals -a. So the number inside is negative of that number outside. The number inside is the negative. My number inside is the negative of the number that's outside. So we take absolute value equations and we split them apart into two pieces. One of them looks exactly the same as the original, just without the absolute value bars. The second one, we change the sign of the stuff that is outside. Always leave the inside alone. That stays the same. We change the sign of the stuff that's outside. And this is how we fix absolute values. So fix absolute value equations first by isolating the absolute value. We can't separate them until the absolute value is all by itself. And then by separating it into two equations. One with the positive and one with the negative. So always start with the isolating, just like we did with the radicals, and then the separating. Isolate and separate. So let's look at an example. Nine minus the absolute value of x plus 2 equals 4. So first off, our goal is to fix this. Fix it means turn it into a regular old linear or quadratic equation. Since there's absolute values, the way that we fix it is by isolate and separate. I'm going to start off just using normal opposite operations to get the absolute value all by itself. So this is a positive 9 in front. So to move it, I'm going to subtract 9. So now I've got negative absolute value of x plus 2 equals negative 5. And then I also need to move that negative sign. And you can think of it as times a negative 1. So I'll divide by a negative 1. And those cancel. And now we have absolute value of x plus 2 equals 5. So now our absolute value is isolated. And this means two things. This means x plus 2 could possibly have two different values. So x plus 2 could equal 5, or x plus 2 could equal negative 5. And then those absolute value bars would change it to positive 5. So x plus 2 could equal positive 5, or x plus 2 could equal negative 5. And now we have two linear equations to solve to get our answers. So for both of them, we need to subtract 2 over. And we get x equals 3 and negative 7. And you should check these problems. Most of them are going to work out fine. There are a couple of trick problems with absolute values that don't work. And it's usually some that have a lot of tricky negatives in them, or some that have squares inside the absolute value. But you should check these to make sure. So 3 and negative 7. The original was 9 minus absolute value of x plus 2 equals 4. And let's see if 3 works. 9 minus the absolute value of 3 plus 2 equals 4. So 3 plus 2 is 5. The absolute value of 5 is 5. 9 minus 5 is 4. Yep. Now if we plug in negative 7, 9 minus absolute value of negative 7 plus 2 equal 4. So negative 7 plus 2 is negative 5. The absolute value of negative 5 is positive 5. 9 minus 5 is 4. Yep, so they both work. This one doesn't have anything crazy going on. So you should check these absolute value problems just to be safe. So always isolate your absolute value and then separate. Don't ever change the expression that is inside the absolute value. What you are changing is the sign of what it is equal to. That is the one that I changed to positive and negative. That's one of the most common mistakes that I see with these problems. So for the absolute value inequalities, and I think this will wrap up chapter 3 here. We're still going to isolate, we're still going to separate, but these aren't equations anymore. These now are going to have less than or greater than symbols in them. So there's two possibilities. If the absolute value of x is greater than a, and this could be greater than, or it could be greater than or equal to. This means two things. So we're still going to isolate and separate, but the greater than sign adds an extra component to the answer. This means that x is greater than a. Remember, one of them is going to look exactly the same as the original. Also, one of them is going to change the sign of the answer. And when you start throwing around negatives in an inequality, the symbol flips. And this is a compound inequality with an or in between. And that is because if you were to graph these two solution sets on a number line, they don't overlap. So negative a would be down here on the left, positive a would be up here on the right. This one says we're going greater than a. This one says we're going less than negative a. So it's an or problem because there's two parts to the answer. So the greater than, or it could be greater than or equal to, is an or problem. And there's usually two pieces to the answer. If it's less than, and I'm going to use a different letter just so it doesn't all start blending together. If your absolute value inequality has a less than symbol, we're going to isolate and separate. So we're still going to have x is less than b. And we're going to have another one with negative b. And when you start throwing around negatives in an inequality, the sign flips. And if you look at these two pieces graphed on a number line, negative b is going to be lower, positive b is going to be higher. And this says we're going to shade above negative b. This one says we're going to shade below positive b. These two guys are going to meet in the middle. So that means this one is an and, because they're going to meet in the middle. So the interval notation would be negative b to positive b. So the less than is an and problem. And there's usually only one interval in the solution. So the greater than is an or, and the less than is an and. And this is going to seem really, really silly. But when I first learned these, I figured out a way to remember them. And you're going to think I'm crazy, and that's okay. Because it works for me. And with the amount of math I know, some of this stuff I don't know because of the math, but I know because of some crazy association that I made. If you look at the greater than sign, and honestly, you're going to think of me completely different after I show you this. You can make an R out of that. It's an ugly R, but you can do it. So, or. Yeah, it's kind of ugly, but it works. You can't make an R out of that, out of the less than sign. But you can make an R out of the greater than sign. So that's how I remember that the greater than is the or, which means the less than has to be the and, because there's one of each. So the greater than is the or. Or means two answers. That's what the union symbol means. It means or. So let's look at one of each of these, and that will wrap it up. So we got absolute value of 2x minus 5 is less than or equal to 10. Less than or equal, I cannot make an R out of that symbol. So it's not my or problem, it's my and problem. So I'm going to separate this into two separate inequalities. My absolute value is already isolated. My absolute value is the only thing on the left-hand side. So I'm going to split this into two separate inequalities. 2x minus 5 is less than or equal to 10. One of your inequalities is always going to look exactly the same as the original. The second one, remember, do not mess with the inside. It's always the number that it's equal to that changes. And with inequalities, when you do the negative, you flip the signs. So 2x minus 5 is less than or equal to 10, and 2x minus 5 is greater than or equal to negative 10. And when we solve these, these two intervals are going to meet in the middle, and we're going to have one answer, one interval answer. So now I've just got two linear inequalities to solve. Just use your opposite operations to get x all by itself. So for both of them, we're going to add the 5 over. So this one ends up as 2x is less than or equal to 15. Here I've got 2x is greater than or equal to negative 5. And then divide them both by 2. X is less than or equal to 15 halves. Most likely, MyLabs Plus is going to want you to leave it as 15 halves. Don't change it to 7.5 or 7.5 or anything like that. Over here, we get x is greater than or equal to negative 5 halves. So if you look at where these two numbers are on a number line, the negatives are on the left, the positives are on the right, so negative 5 halves is going to be on the left. It's got the or equals line, so we color it in. 15 halves is positive, so it's going to be over on the right. It's got the or equals, so we color it in. And think of this as an arrowhead pointing which way to shade. So from negative 5 halves, I'm going to shade to the right. From 15 halves, I'm going to shade to the left. And see, they meet each other in the middle. So if we want to write our answer in interval notation, it goes from negative 5 halves to 15 halves. And then let's get one that has a greater than symbol, so you can see how the greater thans work out a little bit differently. There we go. Well, this one is really different. But really different's okay. Absolute value of 6 minus 4x is greater than or equal to 8. This one's got a little trick in it, so you shall see in just a second. Graphing on a number line is going to be really important here. So this has got greater than. I could make an R with that. That means it's an OR problem. So right off the bat, I'm thinking I'm going to have two parts to my answer here, but we'll see what happens. My absolute value is already isolated, so I'm going to go ahead and separate into two pieces. 6 minus 4x greater than or equal to 8. The first one always looks exactly the same. The second one, always keep the inside the same. Flip the symbol, change it to negative 8. And now I've got two linear inequalities to solve. So minus your 6 over. We're trying to isolate our x. Negative 4x is greater than or equal to 2. Negative 4x is less than or equal to negative 14. Divide by negative 4 and be really careful. Multiplying or dividing by a negative will flip your sign. So now I've got x is less than or equal to negative 1/2. Or x is greater than or equal to, because dividing by a negative flips the sign, and that fraction simplifies to 7/2. So if we look at what this looks like on the number line, negative and positive. So negative is the number on the left. It's less than or equal to. If you think of that as an arrowhead, it tells me to shade to the left of negative 1/2. 7/2 is going to be on the right because it's a positive. It's got the or equals to, so I'm going to color it in. Think of it as an arrowhead, and it's telling me to shade to the right. So yep, this is going to be two pieces. It's an OR problem. It's two pieces. So negative infinity to negative 1/2. Bracket, because we colored it in, it has the or equals line underneath. And then also, I've got a second piece, 7/2 to infinity. Again, a bracket on the 7/2 because we colored it in, it has the or equals line. Your positive and negative infinity, they always get parentheses because infinity is not really a number. Infinity is just the idea that we keep going forever. So infinities, no matter what the symbol is, infinities always get parentheses. So I hope this helps out with section 4 and section 5. Good luck on your test. If you have any more questions about anything that I did not talk about, just email me. I'll be in the math tank on Monday and Wednesday from 12 to 1. If those times don't work for you, just call or email me and we can set up a different time. And I would be more than happy to help you. You just got to let me know that you need some help.